Okay, so let's take a small object of mass m, shown here, shaded in yellow, which is going around in a circular motion, in a vertical circular motion. The radius of the circle is capital R, and let's try and see if the string has a tension at which it breaks. Let's call the tension as T break. If the tension goes beyond T break, the string would break and snap off. So now, without breaking the string, if I have to keep moving this object in a vertical circular motion, what is the maximum velocity to which we can rotate this? Maximum linear velocity or linear speed to which we can rotate this. Beyond that, the string would break. Now, for that, let's find out the tension at the top and the down positions. We know that at the top, when the object is at the top and it's rotating, and this position at the peak, the tension Tu as shown in the figure plus mg is the centripetal force, which is mv, velocity at the top, squared divided by the radius. Now this gives us that the tension Tu is mvt square by r minus mg. Let's keep this as one equation. And similarly at the bottom, when it's at the down position, we know that the tension Td at the down position minus mg would be equal to the centripetal force, which is mvd square by r. Now this gives Td at the down, when it's down, the tension is mvd square by r plus mg. This is equation 2. So if we look at equation 2, it's very obvious that as the velocity increases, this tension would increase more because it has got a plus mg component, this has got a minus mg component. So the tension can be maximum only when it is at this position. Even when it is goes to the little to the left or to the right, what happens is there is an angular component of mg only comes in. If there is an angle theta formed here, then only a component of mg would act on it, and it won't be as high as it is when it is here. So Td given by equation 2 at that position is where the maximum tension is found. So now if we know this T break, or the tension at which the string would break, we can plug it in here in this equation and then see what happens. So this, if we replace Td with T break, then this would be mvd square by r plus mg. Now this gives us m velocity square by r equals T break minus mg. So from this we can find out the velocity d square is nothing but T break minus mg times r by cross multiplying divided by m. Now if we remove the square here, this whole thing comes under root. So this gives the velocity. The Vd is the velocity when it's at the down or the bottommost position for this tension, the tension T break, which means when we plug in the value of T break here, whatever Vd we get, the velocity of the rotation, the linear velocity has to be less than that, because if it exceeds Vd, then the string would snap. Thank you.